Hi everyone and welcome back to Digital Design with Verilog course. So today we will discuss about operators where we left on the previous lecture, right? So I gave you few homeworks like these kind of coding questions I gave you as homeworks, and also few questions were there, assignment questions, that also we will discuss in today's lecture, and obviously we will do few more topics. Okay, so before how will I explain the solutions, I will directly jump into the code and there I will explain the solutions. So let me jump into the code. So these two files are for the demonstrations of operators. So the first one was for the bitwise operators. So these were arithmetic operators, so I don't think much I have to describe about them. But where is the bitwise operator? Bitwise operator is somewhere here. Okay, so I will just uncomment this, and for bitwise operator we need to have a test bench as well. I give you the screenshot of the test bench as well. Okay, so for the bitwise operator the test bench is here. Okay, so like obviously you can make in separate files. I'm making in one file because it is easier for me, because all the operator questions are in one place, so that it will be easier for me. But you can make in separate files. It totally is up to you how you want to make, and like the Verilog code, it is recommended to make in separate files. Okay, of course I am like just teaching you guys, so that's why I'm using like this. So now what we need to do is, I have uncommented the Verilog code, and this one will always be uncommented, and this module also I have uncommented. So basically I will do iVerilog and operators. Okay, so if I do iVerilog operators, it is a bit slow right now, it compiles, no problems. Now let's do VBP operators. So if I do VBP operators, basically it has the outputs, but where is the just hold on. Okay, like it assigns all those things, but we are okay. I don't think we are monitoring anything. Why it is not showing the monitor statements? Okay, oh yeah, sorry, I did not uncomment everything, right? This also should be uncommented. So let me, because the monitor statement was commented, that's why the compiler simply ignored it. Okay, so if I uncomment, so you can basically see, right, where like the outputs are very simple. We are just using the bitwise operators, and it will perform operations bit by bit. So not of x, it is like a reduction operator, right? So it nots all the individual bits, right? If you see, like the LSB is 0, here it is 1, it is 0 1 0. Okay, very simple. Then x and y, what will be x and y? X and y will be again bitwise. 0 0 will be 0, 0 1 will be 0, 0 1 will be 0, here 0, and the last like the MSB is 1 for both of them, that's why it is 1. Okay, so I hope you have understood this thing. What about x or y? X or y, just like even if one of the bits is 1, it will be 1. So the LSB is 0 for both of them, but here this is 1, so that means it will be 1. Here it is 1, so this second bit will be 1, and the MSB again both of them are 1, hence it is 1. Okay, so I hope you can see, like whatever I'm doing, it is just applying the XOR and or not. Okay, I hope like I don't need to explain much. It is doing XNOR here. I hope you know how to do XNOR as well. Okay, so yeah, this was about the XOR operator. Like you can play around with this, you can give different outputs. So this was the homework task assignment for you. Okay, so now let's come to the next one. Next one was for the arithmetic operators. So if I come to the arithmetic operators, so I will just comment this one out. This is done now. So again I have to comment this one out as well. Then I will uncomment the arithmetic operators. So like these are basic things only. I have to obviously explain everything, so that's why I'm doing this. But I like, my expectation is you guys can do it very easily. Okay, with a blast. So this is the arithmetic operators. So like we have to just directly run it. We don't need to call it. Okay, so we don't need to uncomment anything. We don't need a test bench here, because directly inside the module as well I'm doing some monitor statements. Generally this is not recommended, but like we are just coding, we are just learning, so we can do it. But generally it is not recommended to put monitor statements here. Okay, it is recommended to put monitor statements on the test bench itself. Okay, so let us just run this code. Okay, if I run this, you can see basically your A is 101, B is 11, and D is this, all these values. Okay, so so like this, all of A and B are both in binary, and D and E are in decimal. Okay, so the sum in binary will be simply of A and B. So we are adding A and B sum. So 1 0 1 and 1 1. So this one becomes 0 here. Sorry, this one, yeah, it becomes 0. Then I have another 1, and this one is already there. Again it will become 0, and then again I have another 1 and I have 0, so it will become 1. Should be, sorry, okay, sorry, this one, there was 2 ones, right? So again I have a carry of 1, so 1 1 again becomes 0. So ultimately again I have a carry of 1, so ultimately I have a 1 here. Okay, so basic in decimal also you can do. What is this? This is 5, right? This is 5, and what is this? 3. 5 plus 3 is 8, which is, you can see in the binary representation of 8 is 1 0 0 0. Okay, so simple thing. And again difference also you can do. Modulus will be what? Modulus, they are doing of what? Modulus of D and E. So D is in decimal, D is 7 and E is 3. So what will be the remainder? If I divide D with 3, the remainder will be 1. That's why modulus is 1. Division is 2. Division is 2 because we are performing, both are integers, and when we will divide, the result also should be a integer. So it just truncates the like decimal part. Just truncates the decimal part, just takes into effect of the first digit, that is 2. So 7 divided by 3 is 2 point something. So it just truncates the decimal part. Okay, power again, d raised to power 7 raised to power 3 you can do. It will be 343. Okay, and like same for other values as well, you can check it out. Okay, so that was about the arithmetic operations. Nothing much to explain over here. So now let's come to the next one, the unary operators. So like unary operators were very simple only. So this were directly I can run it because monitor statement is here only. So like basic division I'm doing, just unary operators minus negative sign is there, and few reduction operators are also unary operators that we will do later on. Okay, so these basic things you can do, like what will be the value of A is stored minus 4, B is 5 plus 5, and C is minus 2, because minus 10 divided by 5 is minus 2. So basic thing only. So now let's do the next one was logical operators. So this is the module for the logical operators. Now here again monitor statement is inside the module itself. Obviously I have told you it is not recommended, but you can place it. Okay, so now if I run this code, and you can see, right, what will be the logical outputs. So if my A is like A at initially I'm giving A0 B0, so not of A will be 1, not of what is this, not alternate. Okay, same, this is not A, like these two, right, are same only. Okay, not of A and this, right, both are same. If I write this exclamation mark, then A, and or this sign like curvy sign, then A, both are same. Okay, both will yield the same result. Okay, and of AB, basically both are 0, so and of AB will be 0, or both are 0, it will be 0. Then I have equal. If they are equal, then it will be 1. Remember, it is a logical operator. So if any number that is not equals to 0, right, it will be treated as 1. If it is x, then the logical operator is x only, but if it is not x, then it will be something else. So better would be if these values are not 0, if this value is not 0, if this value is 5, even if this value is 5, right, then also it will be treated as 1 only. Okay, 1 means logical true. Okay, just I wanted to clear this confusion so that this confusion is not there. Let's say this A and B are 5 at the end, right, at 40 nanoseconds. Okay, so let me do this, let me recompile this. So okay, why is it not showing the 5? A and B are 5 at the end, it should show. It is only, okay, it is only showing 2 bits. Why? Okay, as the my register is only 2 bits long, so we can make it more lengthy. So we can make it at least 4 bits long. So then now it will be able to store the information about 5. Okay, yeah, now it can store 4 bits. So now if you see, if this is 5, right, and this is 0. Okay, so I am doing logical AND. If I am doing logical AND, even if one of them is 0, and result will be 0. Now I am doing logical OR. Logical OR means assume anything that is non-zero to be 1 except that x or z, okay, that I will discuss. Except that it will be 1. So this 5 gets converted to 1 and this 0 is only 0 only. So 1 or 0 is 1. That's why I get here 1. Okay. Equality, again, if they are equal, it will be 1. If they are not equal, it will be 0. Now let's come to the don't care conditions. So here, right, if I have like x here and if this is let's say 2, then all the results will be x except this. Why? Because this b is 2, right? And if I am applying logical OR, then b assumes, like the compiler Verilog assumes this 2 to be 1. So 1 or anything will be 1 only. I hope you understand. 1 or anything is 1 only. 1 or 0, 1 or 1, it will always result in 1. So this will be always 1. Okay. Then equal to, this will be 0. Okay. Now let's come to this one. Okay, like this one. Again here the OR is x equals to is x because it will not be able to evaluate. Not alternative is x also, but AB and of AB is 0. Why? And is 0 because even if one of them is 0, right, this B is 0, that means 0 and anything is always it always results in 0. So this will be 0. Next I am at this expression. Now both are x, okay, both are unknown. So obviously all the results are unknown only. If you can see, both are high impedance, all the results are again unknown. Okay, so I hope you got an idea about the logical operators. Okay, you can play around, you can understand this more logically. Okay, so what was the next one? Next one was case equality. So let us uncomment the case equality. So what is the case equality? If I can find it out somewhere. Yeah, this one is the case equality. Okay, so right now I don't have any assign statement, monitor statements here, so I have to uncomment from here case equality, this one. So this is the test bench for case equality. Actually I didn't have enough time, so I was not able to write like the monitor statement separately. At that point of time I written it same only, so like it will not make any difference. Generally this is what we follow. We write the monitor statements outside on the test bench. Okay, so now if I again compile and rerun this. Okay, just like case equality and what is the difference between equality, and case equality, that is what we will see. So this is just normal logical equality. If my A and B both are like same and they don't have any x or z, that means it will evaluate to 1. Yes, it is evaluating to 1, and case equality is also evaluating to 1. Logical not equality is evaluating to 0. This is evaluating to non-zero. Now one of the value has x in it, so logical equality evaluates to x. Even if one of the value has x, it will always evaluate to x. But case equality evaluates to 0. Why? Because this is x and this is 0, so they are not equal definitely. So that's why case equality checks everything bit by bit. It checks everything bit by bit. So it is not like they are not same, so this will be 0. Again, logical not equality, it will treat as x because it does not understand what is x. Okay, that's why they are synthesizable. Case not equality, again it will evaluate 1 because they are not equal, because it checks everything bit by bit. X and 0 are not equal, so it will be 1. What about the last one? Last one is this one. So A is this and B is this. Okay, so now your logical equality, even though they are identical, it will evaluate to x because this x can be anything. That's why like logical equality does not evaluate for don't care values, but case equality will evaluate. It is evaluating to 1. Why? Because they are exactly same. Like it just checks bit by bit even the x values. Logical not equality, again x. Case not equality 0 because they are exactly same. Okay, so I hope you have understood the difference between logical equality and case equality, logical not equality and case not equality. So this will be logical not equality and case not equality. Okay, so let me just comment this one out. Let us move on to the next portion of our code. So next portion was relational operators. So if I now move on to the relational operators are here only. Okay, so these are the relational operators. So let me just check whether we have, yeah, we have a test bench for relational operators as well. So this is what I am simulating. So let's check here. Let me first compile the code. Okay, and let us see the outputs. So what are relational operators? They just check whether a number is greater than or less than or equals to. Okay, something like that, greater than equals to or less than equals to. So here if I see, like it is checking a less than or equals to. Okay, it will check if a is less than or equals to b, then it will evaluate to true, that is 1. Logical 1 means true. So here initially my a is 4, b is 3, so it is evaluating to 0, which is absolutely correct because a is actually greater than b. This is evaluating to 1, again it is correct. So this portion is correct. Let us check for the x and y. So here x, right, is 1101 and z is 1xxx. Okay, so basically what we check is this bit is 1, this bit is 1. Okay, so this will evaluate to 1. Why this will evaluate to 1? Because let's say this is evaluate, sorry, I am talking about x on, okay, we are not talking about z for now, we are talking about x and y. So this is x and this is y. So of course this bit next to the MSB is 1 and for x it is 0. So of course y will be greater than x, that is getting shown here. Okay, now let's discuss about y. Okay, so we are just doing and why we are doing and of y and z. Okay, I think this bitwise and, right, it should not have been here, it should have been somewhere else. I don't understand why is this here, this should have been somewhere else in the bitwise and operation. Okay, that is my bad, this should have been somewhere else. Okay, so sorry for that. So only these three things will be there, right? Less than equals to, greater than, greater than equals to. Okay, also you can check less than as well. Okay, you can check less than as well. I will just write that less than. That is my bad, I didn't input it, so I will just do the same only. Y less than x, y less than x, y less than x. Okay, and let me remove the z. Z is actually not required, so I will remove the z, and from here as well I will remove the z. Z is actually not required. Okay, so this here as well, z will not be required, and in the module as well I will remove the z. Z has been removed from here as well. This will be y less than x. Z will not be required. Okay, x, y. Okay, it is all okay. It was already here, but for some reason okay, fine. X, Y, A, B, that's it. Yeah, sorry for the interruption. Like I just forgot to, like, this was for some other operator. This got caught here. That is the problem. So this will be dot y less than x. This will be y less than x. Okay, this will change to less than x. So let's see if whatever I have coded is correct or wrong. Okay, so let me compile this. If I have coded it wrong, some error will be there. Error is here, right? Port 5 z of relation. Okay, this I have to save first. If I don't save, then like it still compiles on the previous one. It still has port z here. This will be y less than x. Okay, what is going wrong here? Okay, this will be LT, right? This will not be same, this will be LT. And there are port Z is not a port of, okay, here if I see port Z, okay, yeah, Z is not a port, obviously. Z we have removed, so we can remove it. Yeah, now I think it should work. Yeah, now it works. So now, like as I was explaining, so I hope you understood a bit of like how to code as well. So here if my y is less than x, which is false here, y is greater than x, so this will be 0. Now here if a is 2, b is 5, then again it will evaluate accordingly. Okay, let's see like here, right, I should have put a comma as well. Did not put a comma here, that is my mistake. Should have put in a comma here. Let's see for a case where my bits are like x, okay, unknown. If my bits are unknown, will it be able to solve? Okay, so let's do this. Extra, like how much size is, okay, this is 4 bits, right? Okay, I've given here how many, 5 bits, that is bit extra. Okay, let's delete this. Now it should be fine. So if you see, right, few it is evaluating x and few it is evaluating 0. Like x and y are anyways like they are. Let's do it for x and y for z. Okay, let's do x and y for z, and let's do a and b for x. Okay, so we can see like it will not evaluate. Okay, the greater than, less than, it will not evaluate. Of course I also don't know everything, I also try out on the code and I see. Okay, so you can see like it will not evaluate if even if one of the values is x or z, right? It will simply not evaluate, it will just give up, and it will just say it is x. Okay, result is x. So I hope you have understood about relational operators. Okay, so let me now comment this thing. Let me now comment out this thing, and let me move on to something else. Okay, so the next one was reduction operator, which, like, although I have explained previously as well, we will see it once again. The reduction operators. So where are the reduction operators? These are the reduction operators. Okay, so these I think will require a monitor statements. So yeah, this is the reduction operator. So reduction operator is nothing, just it will operate on its own. So if I do I Verilog and then run this, so you can see, let me just change this to 0t so that there will be switch. Like I have made it 0t so that, like this, right? Previously this space was coming. This 0 means how much space I want to give after this equals to sign. Okay, that is what this 0 means. So if you have a higher number, this will give more space. Okay, or if you give like no number, the default size, right, of time it will take as space. Okay, default size of time is 32 bits, what I remember, 32 or 64, whatever it was. So accordingly it will give that space. Okay, so yeah, that's about it. So now if you see, yeah, my x is this. If I am doing reduction and basically it will do 0 and 1, 0 and 1, so it will be 0 only. Reduction or even if one of the bits is 1, it will be 1. Reductions or, I hope you can understand. Reduction x naught also you can do, just simply take the naught of the answer and that will give you as x naught. Okay, so pretty straightforward, nothing like fancy stuff, like you can see the results and the answers. Okay, so that was it. Now let me comment this one out. Okay, now let's move on to the last one. Last one was the most difficult one, and I have explained as well, the shift operator. So shift operator is like the most interesting one as well. So let me uncomment this shift operator. So we have like okay, this is the shift operator. This is the test bench for shift operator, and like we have arithmetic shift, and we have our normal logical shift. So first we will see logical shift, then we will discuss about arithmetic shift. Okay, so let's now compile. Okay, some syntax error is there in the test bench, I believe. Yeah, test bench has some syntax error. Okay. Okay, reduction operators should be actually, okay, this should not be there, right? Yeah, this should be commented out first, then this should be called. Yeah, now I think it should work. Okay, still 110. What are the problems? 9 and 10. Okay, should work. This should not be any issue. These are off, right? Yeah. So just checking what is the missing code for the string. No string is there. Page 110 code is there actually, but I think multi-line string won't be allowed. I think multi-line string is not allowed, I think. So now if I do this, yeah, so that was the problem, right? If you press here enter, like it does not allow this. I have explained previously as well, multi-line string is not allowed, so you will not be able to use multi-line string. And like, of course, I don't know everything, right? I also like see the code, what is wrong, then I try to compile this. Okay, so I hope you understood the here what was the bug. Multi-line string is not allowed, just you have to have the string in single line. Okay, that was the problem. Now if I see the outputs, so you can see the outputs, right? So my x is 1100, in decimal it is this. If I do logical right shift 1, if I do logical right shift 1, basically what will happen, this everything will be shifted by 1. This 0 will come at the end, this 1 will come in the second last position, this 1 will come in the third last position, and 0 I will fill with 0 in the MSB. So if I do logical right shift 1 here, I am seeing like it is getting what? It is getting halved basically. Simply it is getting half, that's it. Okay, what about left shift? If I see left shift, here it is 100. What is happening basically, this one, right, this one is going to the dustbin. Okay, to the left, I don't have anything to the left, so simply it will go to the dustbin. So this second MSB will come here on the MSB position, then of course all zeros will come, right? And the last bit is empty, so I will fill it with 0. So that is what is written over here, 1000. So it is basically 8. So there is not a fixed formula, right? Like this was 12, there is not a fixed formula for left shift. Okay, although there is, I will not, I don't want to tell you that formula right now. Simply just for right shift it is divided by 2. Okay, but for left shift it is not simply multiply by 2, not like that. Okay, so if you see here as well, 6, again if I do left shift 1, it is divided by 2, that is 3. But for right shift, sorry, if I do right shift 1, it is 3, but for left shift it is 1100. How much is it? It is simply 12. So here in this case it becomes double. Okay, in this case it becomes double, but sometimes it may not become double. Just be careful about that. Like here, right, it is 9. If it is 9, if I do right shift 1, right, basically in binary this is okay, in here it is 1001. So this one information is anyways gone, this will go away. Basically this one will come here and everything will be filled with zeros. So basically it will be 01100, so it will be 4. So of course we ignore the trunk, the floating point. After this we just take into effect of the integer portion when we do the right shift. Okay, left shift, again if I do left shift, then this one will come here and everything will be 0. So basically it will be 2. So it is not very simple, just like multiplying 2. Okay, it is not like that for the left shift case. Okay, if I do 2 times left shift, then it will be like 2, it will be here. Okay, that's it. So here if x is 0, then if I do right shift left shift, everything will be 0 only. Okay, if I will divide by 2, it will be 0 only. Okay, so if x is 14, then if I do right shift, it is 7. You can see, right, there is a pattern here for right shift, but for left shift there is not an exact pattern. Again it is 12 only, here it is 12 only. Okay, so yeah, I hope you have understood the right shift and left shift. Okay, now let's discuss about the arithmetic shift. Let's discuss about the arithmetic shift. So this is the arithmetic shift. Now, like I have told you, right, it is only it only comes into the action, like the result is different for a normal logical shift to arithmetic shift only when the numbers are negative. If the numbers are not negative, it will not come into action. Okay, so let me run this. So now if I see my A is 5, B is minus 20. If B is minus 20, right, in one's 2's complement representation, it will be stored like this. Then I will do the right shift, keeping the MSB intact. Okay, keeping the MSB intact, then I will do the right shift, and then if I take the complement of it, my final result will be minus 3 only, because I am shifting by 3. In the previous lecture, I have explained very well how we are doing it. Okay, explained very well. If I just go back here, I think I remember where is the arithmetic right shift. What is the arithmetic right shift? Yeah, I've explained very well with with exactly this example only. With this example only, I have explained. So I hope you understood what is arithmetic right shift. If you see, if A and B both are positive, right, and if I'm like moving by B by 3 bits, it will not be anything different, right? Simply what will happen, what is B is 15, so 15 divided by 2 raised to power 3, 15 divided by 2 raised to power 3 is 8. It is almost 1 point something, so basically whatever is coming after 1, that gets truncated and it is only 1. Okay, but what about C? So what is C? C is equals to A plus B arithmetic ratio 3, so it is something else only. Okay, we don't need to take care of the C value. Just I gave you that expression to evaluate, like to solve, basically to frame a question, that's it. So again, when B is negative, right, so here, right, I cannot like you can do that formula again, 2 raised to power 3. Okay, you can again do that formula. If you divide by 2 raised to power 3, right, it is 20 divided by 8. 20 divided by 8 is 2 minus 2 point something. So then it does is like, what it does is it basically divides minus 20 by 8. If it divides minus 20 by 8, that means it is minus 2 point something, right? So it rounds off to the nearest integer. In that case, it is minus 3. Okay, but I will not recommend you remembering that. Remember this concept, that it stores in the 2's complement format. Like this is what it actually does. Then the first MSB is the sign bit that is stored, that will not change, but all the other bits will shift. Okay, and then you will find the 2's complement of that. So if you see, minus 8 is over here. Now if I right shift this by what, 3, then it becomes what? Then it becomes minus 1. Why? Because what I am doing is I'm basically doing minus 8 divided by 2 cube. So it will be white cube, because I am shifting by 3 bits. If it was if I was shifting by 2 bits, then it would have been 2 square. Okay, so I hope you have understood this point. So it will be B equals to minus 8 divided by 2 cube, that is 8. So it will be minus 1 only, and this is just a result, C equal to 7. And if B is 0, then it doesn't matter, right? Like whatever you do, it doesn't matter, it will be 0 only. Okay, so I hope you have understood the difference. If you ever feel like you need more understanding, please go ahead, write the code, put the values in, then you will understand this more. Okay, so that was about the arithmetic shift. Okay, so I think almost we have covered everything. Shifting operator, arithmetic shift also we have covered. So okay, I think here, right, I forgot to put the arithmetic shift here. Okay, so now what we will do, I gave you a few questions as homeworks, those we will do right now. Okay, so let's go to the questions. So this was the first question. So we have to find the values of A and B from the given expression. So A is equals to Y right shift of 1B1, and B is Y right shift 3 sorry, this is arithmetic right shift of 1B1. Okay, if given that the initial value of Y is 1101, okay, and Y is a signed number. So Y is a signed number, remember, right? So if Y is a signed number, for normal right shift, right, it will not, like, there will not be any change. Basically it will be treated as unsigned only. So what will be the result? The result will be 1101, right? So I have to right shift 1, okay, by 1. So this 0 will come here, this 1 will come here, this 1 will come here, and this position will be filled with 0. So my result, my answer for the first case will be 0 1 1 0. Okay, this will be the result for the first case. Okay, so the 0th position will be filled with 0 for normal right shift. Okay, what about arithmetic right shift? What about arithmetic right shift? So if I am doing arithmetic right shift, right, so this result is Y right shift 1B1. Okay, okay, now if I am doing arithmetic right shift, then what will happen? Then this, right, this is in the 2's complement format, right? This number is stored in the 2's complement format. Okay, this number is stored in the 2's complement format. They have mentioned y is a signed number. So I will just store the MSB. Okay, then I will keep the number, then I will right shift everything by 1. So this will come here, this will come here. So it will be 0, 1, and obviously it will be like here it will be 0, right? This will be filled with 0. Okay, and what will be this? Okay, so this, right, this will be filled with 1. Okay, so this will be filled with 1. No, sorry, this will not be filled with 0. Sorry, I told you, right, previously whatever the sign here is, that is filled with the remaining number. So it is this 1110. So now what we do, we simply do the addition of 1. Okay, so first of all I will like if I want to write like talk about in decimal, what will be the value? So in decimal here the value will be simply what? The value will be this is 4 and 2, so this will be 6. Okay, and here what will be the value? So this will be minus 6 basically, not minus 6, sorry, this will be plus 6. Okay, so this will be what? So first of all I have to, like if I want to talk about decimal, right, in decimal if I want to discuss, so this will be like as its MSB is 1. Okay, that means it is negative. Like here, right, after doing the logical right shift, the MSB becomes 0. So if it becomes 0, even though it is a signed number, so if the MSB is 0, that means its sign is positive. Okay, so now I will do this. Now I will like as the MSB here is 1, that means what? That means it is a negative number. So if I want to write in decimal, how will I write in negative number in decimal? So basically I have to take the 2's complement. For taking the 2's complement, this becomes 0, 0, 1. Okay, then I add 1, this becomes 0, 1, 0. So this is the actual number. Okay, that is 2, and obviously the MSB was 1, that's why the sign will be minus 2. That's why the sign will be minus 2. Okay, so this is what the sign will be. Okay, this is the answer, minus 2 and 6. So this is the theory. Let's see whether we will get the same result in actual code or not. Okay, so let me just turn this on. So this is the code, I have made the question. Okay, so now if I just run this code, right, like it is ready, I have cd to my I've changed my directory to my project location. If I just run, because the display statement is here only, so we can directly run this code. Okay, so I'm directly running this code. Okay, so just hold on, let me, okay, something is wrong. So let me do this Verilog questions and test bench. Test bench is here, it is not doing anything. Okay, test bench is not doing anything, just I have to run these things, that's why I have to call the test bench. Okay, so then I do VBP. So if you see, y is 1101 as I have shown in the question, right, y is 1101. Now if I choose my, like what will be a is equals to what? A is logical right shift. So what happens in binary, if you see, whatever we have learned, whatever we have derived, that is the case. And remember your y, right, is a signed number. This will only be correct if you write here signed. If you don't write here signed, it will not show you the correct result. Okay, because Verilog has to understand whether this variable is signed or unsigned. Okay, so that is the case here. So a value is this and b value is, like if I am doing logical arithmetic right shift, if I am doing arithmetic right shift, it is 1100. Isn't that what we derived? If I should show you, if I just show you here, that is what we derived, right? This was the value of b. Okay, and this was the value of a. So I hope whatever we have learned theoretically, practically also you can see that is coming. Okay, and obviously now if I want to come back to this from this to decimal, right, obviously Verilog understands it is a signed number. So here it is stored in 2's complement format. So here it will be in the decimal format. So it understands this is the sign bit. So minus 2, then I have 2 here. Okay, so I hope you have understood the arithmetic right shift and logical right shift. So this is a very, very good question. So I hope this got clear. Okay, so now let's move on to the next question. So next question we will move on. So next question is here. So if p is a 10-bit vector, now I hope you understand what is a vector. basically multiple bits. Okay, find its value for the expression this. So what is this? This operator is concatenation operator. Okay, so this operator is like, what is this doing? This is the repetition, right? It repeats this one, whatever is inside this, it repeats. So basically here 2 1 1, so twice repeat 1, so it will be 1 1. Then I have, like, if I want to show this properly, then I have this 1 0. So this, right, is a concatenation operator, so it will concatenate all the bits. So this will be 1 0. Then I have 1 0 1. Then I have x1. Okay, so this will be x1. Basically, why am I showing, like, it will not make any difference, this underscore will not show, will not make any difference, but for better readability, to understand this thing, I am showing it like this. So now let's go back to the code and see the same. Okay, so if I go back to the code, this is the question 2, and if I uncomment this, so I'm doing the same, whatever was there in the question, I'm doing the same thing. We are replicating and concatenating. So now if I print, right, display the statement, we will see we are getting the same result, 0x1. So sorry, 0, why is 0 there in front? 0 should not be there, right? Okay, as p, right, is a 10-bit number. Was it here 10 bits? This is 2 to 4 and okay, it was 9 bits. That's why this 0 came. P is not supposed to be 10 bits, right? So that's why I have to change this to 8, because this 0 got padded. So p is 8-bit number. So then the result will come out to, although the 0 does not matter, it should not show 0, but still. So now I hope you understand. x1 is there, then 1 0 1 is there, then 1 0 is there, then 1 1 is there. Okay, so I hope you have understood. Like, this is pretty straightforward. It is not a 10-bit vector, it is actually 9-bit vector. Actually, okay, if it is a 10-bit vector, right, that was my mistake. If it is a 10-bit vector, in the question if they have given 10-bit vector, then I have made a mistake. Like, although it does not matter, of course the starting bit will be 0, that is on my behalf. So here, right, this, right, before the x, as it is a 10-bit vector, so I have not provided what will be the MSB. So obviously Verilog understands the MSB will be padded to 0, because 0 does not make any difference. Okay, so this number will be 0 at the start. Okay, now people will get confused that this is hex number, so this is not a hex number. To emphasize that, I will write here 10b 10 tick b. Okay, to emphasize this is not a hex number. Okay, now people will be understanding this thing. This is a 10-bit number. Okay, so now let's move on to the next portion, basically this portion. Find the value of q for the following snippet. Okay, if m is equals to 2b10 and n equals to 2b1x, and assign this. Okay, this is a ternary operator, like it operates it operates on 3 things. Okay, so I have to check whether m is less than n. So will it be able to check m less than n? No, right? Again, I have told you today itself, if even if one of the bits is x, it is ambiguous. It is ambiguous, right? So basically it will not evaluate. So it cannot evaluate. It cannot evaluate. Hence the result of q also will be ambiguous. This is ambiguous. Hence q also will be x, it will be also ambiguous. Okay, so let's show this in code itself. So if I want to show you in the code itself, let me show in the code itself. Okay, so here this is the question 3. Okay, this is not the question, this is the question 3 only. Yeah, so if we just compile this and run this, you see, okay, one mistake I made. Actually what happens is, like if I see, right, I'll show you one thing. Let me just come back to the code. Although this is ambiguous, right? One, like Verilog is very smart. What it understands, either it has to go here or here, right? So what it sees is, like, the first bit anyways is 1. So what the Verilog code will do is, it will choose the first bit to be 1, okay, and the last bit to be x, because it can be the 0 or 1. Okay, it does not obviously we cannot say, because we don't have a result from here. Okay, So that is the only thing. Like of course I also forgot this answer. Okay, I also forgot this answer. I have to also sometimes check in the code, but generally, right, the result is ambiguous and then like we don't get output, but this also can be the case. Okay, so I will just show you for different cases. Let's say if both were 1, right, then what will happen? Then the result will be 1 1. Okay, because it is not ambiguous anymore, even though the m less than n, that is ambiguous, but either way I go, the result will be 1 1. So if I compile this, you see q is 1 1, even though m and n are by themselves are ambiguous. Okay, so that is one thing. Now let's say if I made this 1 0 and 0 0. Okay, so now if I compile this, right, it will again show x q is xx. Okay, because it is totally ambiguous, because it can be 1 0 0 0. So overall, like the absolute correct answer should be it is xx, because sometimes for some values of this, right, true and false, it can be 1x or 0x, something like that. So overall, like the correct answer is ambiguous. Okay, q will be x, but if they sometimes if they want to dig deeper, you can say it will depend, right, on the values. If this value is 1 here in the first bit msb, this is also 1 msb, so that bit will be fixed for q. Other bits can be ambiguous. So like that you can answer, right? Just I will write here the bits which are same in both true and false condition, those will be shown else x. Okay, so just in short, I want to explain this thing. So in the same position, which is same in the same position. Okay, that is also very important. If they are same in the same position, then there will be no problems for those bits, but for other bits it will be x. Okay, so I hope you have understood this point. Now let's move on to the next question. So next question is for equality operator. So for equality operator, again if you see here, my b has like x in it and n has also x in it. So obviously normal equality will result in a x and case equality will result in a 1, logical 1. Why? Because they are exactly same, x and x are exactly same. So let me show you in the code itself. So if I come back to the code and if I just run this, okay, I Verilog then VVP, you see case equality is obviously giving logical 1 and the normal equality is giving x. Okay, so I hope you have understood the result of this question. So let me come back to my notepad. So again something similar, I'm doing a or b. So we have to find q for a or y, so not b, a or y. This is again very simple, right? So this is what this is bitwise or. Okay, this is not logical or. Logical or has 2 dash, bitwise or has a single dash. So don't get messed up with logical or and bitwise or. So again result will be very simple. 1, this will be 1, this will be 0, this will be 1. Okay, 1 1 0 1. So I don't think we have to show it, but I think if you want to see, we can see real quickly. Pretty straightforward. Bitwise or we are doing. Okay, so here just I will just quickly show you that this is the code. So if you see, I'm getting 1 1 0 1. Pretty straightforward, nothing fancy here. Okay, so let me compile this thing. Okay, so let me come back to the next question. So this question we had, you have to evaluate the value, right? So here we have to evaluate the values of C, F in the following snippet. So what am I doing? Like they are doing some arithmetic operation. First C is doing a plus b. If I am doing a plus b, it is very simple, right? It will be 0 1. This will be 1 1. The 1 will come. This will be, yeah, this will be 0 1 0 0. Okay, so ultimately this will be 4, and in decimal and binary I have written. So F will be d by e, d by e. So d by e, what is d? D is basically 7 and e is 3. So ultimately this will come out to be 2, because it will truncate the floating value, decimal value, it will just take the integer part. Okay, so let us do the same like in the code itself. Like this is just a simple arithmetic operation. So this was the last question basically. So let me, okay, there is some syntax error. Okay, this will not come here. Yeah, now I think it will be fine. So you can see F is 2 and your C is 4, as you can see here. Okay, so not that difficult, pretty simple only. So now we will discuss about like we have discussed the assignment solutions. Now we will discuss about few more modules. Okay, we will discuss about 4-bit adder and ripple counter. So this one already you have understood, like what is a mux, how to design a mux. Okay, so using logic, now I hope you understand how I can use mux using logic operators, right? Logical operators. So now I hope you understand what is this, what is this, what is this. Okay, this is a 4:1 mux. If this is a 4:1 mux, what will be the logical expression for the mux? Okay, I hope you remember the logical expression for a mux. For a 4:1 mux, for a 4:1 mux, I will have two select lines, right? So if my output, right, let's say my output is out. Okay, it will be S0 bar, S1 bar, I0. I hope you know all this. Then it will be S0, S1 bar, I1, S0, S1, S1 bar, S0 bar, S1 into I2, S0, S1 into I3. Okay, so that is what like exactly it is doing, right? Ultimately it is doing OR, and here it is doing not of S1, not of S0 and I0. So these are AND only. Okay, so this is the same thing only what is doing. So I have previously written this at that point of time. I think you were having some doubts. I hope all those doubts have got cleared now. So this is the representation of a data flow representation of a mux. Okay, data flow representation. I have given you the gate level modeling. Now this is the data flow level modeling. Okay, we can use conditional operators as well. So the same code, right? Like the same data flow code. This is also data flow level modeling, but we are using conditional operators. So what does it evaluate? So first I will evaluate S1. Okay, if S1 is low, then I will go here. Sorry, if S1 is low, right, I will come here. If S1 is high, I will come here. So what does S1 low and high mean? If S1 is high, that means S1 is 1. So the MSV is 1. That means either it can be I3 or I2. So here, right, if you see, if wherever S1 is high here and here. So it can be either I2 or I3. So that is the same thing what I am doing. So I am first checking S1. So if S1 is high, that means I will be lying here. Either it will be I3 or I2. If it is low, that means I will be lying here. That is, it will be either I1 or I0. Okay. So that is the first point. Second point is, now once I come into this operator, conditional operator, now I check another condition, S0. If S0, like let's say if S1 is high, so if S1 is high, I will come here. Now I will check if S0 is high or low. If S0 or S0 is high, that means I will choose I3. That means S0, S1 both are 1 1, that is it will be I3 only. If S0 is low, that means I will choose I2. So that means if S0 is low, that means it is 1 0, that's why I will choose I2. Okay, I hope you are understanding the point here, and same for here as well. Okay, so this is how we can nest. This is known as the nesting of conditional operators. So we can nest, right? We can nest conditional operators. Okay, so so if you see, like why we will use this and why we will not use this, like this is much more elegant, right? It looks much good, okay, than this. Like the expression is so long. Now if you increase another select line, this expression will become more longer, but this will not be that long. Okay, so that is just like why we can use this. It's totally up to you. Both will work totally fine. Okay, it depends how you want to implement. Okay, that is the main thing. Now let's discuss a bit about full adder. So up until now, whatever we have used, we have like whatever full adder we have designed, we have designed for a ripple carry adder. Okay, what does ripple carry adder mean? Ripple carry adder. ripple carry adder basically means that the carry, right, is rippling throughout the full adders. Okay, this is the full adder one. First I calculate the 0th bit addition, then I give the carry to the next full adder, then it propagates, right? So basically it ripples throughout the adders. Okay, up until now what we have been studying. So just wanted to give you a new code, like this is the like code for full adder. Okay, this is the structural code. I hope you understood like how are we using structural. Basically there is a module named full adder. Okay, and which calls, like there is a module named full adder 4-bit which calls in turn each 1-bit full adders, which has output as S0 and 1. Okay, which gives the carry and the S0 sum, and of course input it takes as carry in and the two inputs A and B. Okay, so this is how we propagate, like whatever is written here, that is what we're doing, and we have already coded a full adder, so I hope I don't need to explain this. Okay, so just want to give you a bit of glimpse on what will come. Okay, this is the behavioral modeling. Okay, just want to give you a bit of glimpse on what will come next. If you understand the code very well, if you don't understand, ignore it for now, because we'll understand this later on as well. Okay, but I hope like I have already explained you this always and this concatenation operator, so you can understand. So whenever if A, B or C in the input carry is changing, that is this, right, then I will calculate, else I will not calculate. So it basically calculates whenever input changes, else it stores to the previous value. So this C out and S are both reg. Okay, C out and S are both reg, you can see, so they will store the previous value. They have to be reg. If you see here right, everything is wire, because this is more like a data flow level modeling, and once we are inside always, right, they have to be reg. That's why this is a behavioral level modeling. We will discuss behavioral level modeling in detail. You don't have to worry about it anymore, like a single bit. Okay, we will discuss about this. So now this is always ABC in C out S. Okay, so like now what we're doing, just we're directly adding, right? So from this code, why am I showing this is you will not be able to understand like what is the hardware in behavioral level modeling. We don't specify the hardware, compiler itself decides the hardware. So I'm directly writing A plus B plus C in. So it is directly doing the addition. Okay, so here, right, I don't mention what kind of hardware needs to be used. Okay, I don't mention. It will automatically, the compiler will automatically synthesize a hardware when we'll go to the synthesis part. Okay, so that is the difference between behavioral and this structural or data flow. So just shown you this example of behavioral to explain you the difference. Right now I hope the difference is more and more clearer, and don't worry, it will get more and more clearer as we move along. Okay, so this is the like 4-bit full adder. Like we can do the same, right, in 4-bit full adder as well. Okay, like this we can do assign, do the same. Okay, but like this is not preferred generally. Okay, this is not preferred because here, right, we're not telling what kind of hardware to use, so this is not preferred. Okay, this type of coding is not preferred. Okay, not preferred. Although this is also data flow level modeling, we can do these kind of things in data flow and in behavioral as well, but we don't prefer it because here, right, I'm not mentioning what kind of hardware or that to use, right, it is directly adding it. So internally Verilog will use some address or something. Now just one more thing I wanted to explain to you guys is there is a concept named as 4-bit full adder with carry look ahead. So a 4-bit full adder performs addition of two binary numbers along with input carry. A carry look ahead improves the speed by generating carries in parallel using propagate and generate logic. Okay, so of course, like I don't have time to explain the generate and propagate logic. This has been taught in our digital electronics course, but basically, right, what we do, we have these bits, right? So with these bits we develop a logic equation that can directly tell me whether I will have a carry here or not, whether I will have a carry here or not, whether I will have a carry here or not. That is Cn1, Cn2, Cn3. Directly I can tell with all this bit information whether I will have a carry or not. Okay, so that is what we do basically. So I will not like tell you the logic here, like it is written here textually what we do actually. Okay, I will just tell you the implementation. Okay, so this is the logic for the carry of the first bit C1. Okay, this is the logic for the C2. And what is G? G is generated here. It is A and B. Of that, I is the bit position. Okay, and what is P? P is the propagated logic, that is simply sum. It is A or B, that is the sum, right, of that particular bit, right? So P is very easy, but we have to develop a logic for carry that we developed. Like for each bit position, what will be the carry that we have developed, and that is the code here. Of course, I'm not explaining you the logic. My expectation is in digital electronics it is already covered, so I don't want to repeat it again. Okay, now we will come to ripple counter. Okay, so for ripple counter we will be using T flip-flops. Okay, I have taken this example from the book Samir Palnitkar, so you can go through that book. Like there they have explained like how does a ripple counter, all those things work. Okay, don't have to worry if you don't understand anything from here, because this will be taught to you in the behavioral modeling, because they took example. That's why I have to like I'm taking this example as well, using whatever we know. Okay, so basically we will design 4-bit ripple counter using negative H D flip-flop. So negative H D flip-flop basically is first, we use first T flip-flop, which in turn calls a D flip-flop. So I hope you know how to design a T flip-flop with a D flip-flop. So I hope I will not explain that. Okay, my expectation is you know how to design a T flip-flop with D flip-flop. Just I will show you the code. I will just show you the code that how we are implementing, how we are making the counter. Okay, the logic I will not explain here. We will study D flip-flop later. Okay, while we are studying the behavioral logic, don't worry about that. For now I'm just showing you how we can use the hierarchical level of modeling. So we are designing a 4-bit ripple counter, okay, with T flip-flop. So basically the Q0, Q1, Q2, Q3 will all be here. That is the Q0, Q1, Q3, Q3. Okay, so they will be input to the T flip-flop. We'll need a clock. So as we have to generate a clock, so the clock will be generated by what? Clock will be generated by the test bench. Okay, that is why test bench is there. Test bench generates the extra signals like clock and all those things. Okay, so clock will be given here, and obviously clear also will be given by the test bench. Okay, so I hope you like understand how to like do the 4-bit triple carry counter. So here we have T flip-flop, the LSB is going here, then I have a clock, then clear. So okay, one thing is there. So this goes here, clock input, like this Q0 also goes into here, right? So that's why like the clock and Q0 both go here. Like basically the Q0 goes here for the next stage. Not the clock doesn't go. The clock doesn't go. The Q0 goes. That's how we make the counter. Okay, I hope you remember the concepts. So the Q1 will go to the next stage of the flip flop. Next to the clock of the next stage of the flip flop. That is what is happening over here. So Q0 is going to the clock of the next stage of the flip flop. Clear bit is same for all of the flip flops. Then Q1 is going to the input of the next stage of the flip flop. Q2 is going to the input of the next stage of the flip flop, and ultimately I'm getting Q3. Okay, so I hope you understood this part of the code. How we are implementing T flip flop? We are just implementing with a negative H D flip flop. Okay, so this is how we are implementing the D flip flop. If you don't understand this, don't worry. Like this is the data flow level of modeling. Okay, so if you don't understand this, don't worry. We will come to this once we will study about behavioral level of modeling. Okay, but ultimately I hope like you know what is the state table for D flip flop, and from there you can design. Okay, that is my expectation. Logic, you know. Okay, so like the concept is written over here. Like if you have forgotten the concept, you can quickly read through this. The same concept is written over here. It is a 4-bit ripple up counter. So basically it will go from 0 to 15. Okay, so and if reset any time, right, it is a active high reset. If anytime reset is high, then all the bits will toggle to 0. Okay, so this is the work of a like ripple counter, and the information about T flip flop and the information about D flip flop, what are the states, all those things are given over here. So now we will come to the code, and I will show you all the examples that we have discussed today. Okay, so let me quickly go to the code. Let me show you. Okay, so these are few basic examples. So this one was the first example, right? 4:1 mux. Okay, 4:1 mux with a simple logical operators. Okay, bitwise operators, not logical, bitwise operators. So if I just like I have developed a test bench. Okay, so if I just like now as I have changed my file, so I have to change my directory again because my directory has been changed. So again I will do change directory cd. Okay, then I will do I verilog basic examples dot vbp, then I will do basic examples test bench dot v. Okay, so it has compiled, no bugs, so no errors. So again I will do vbp basic examples dot vbp. Okay, so now like whatever output you expected, you will get that only, because when select lines are 0 0, that means I will select I0, that is 0 0 1. When select line is 0 1, I will select the I1, that is 0. Okay, sorry, it is 0 1. It should select the I1 actually. Why is it selecting 0 0? Yeah, one mistake I realized that this code, right, is only valid for a 1-bit number. Like if my I0, I1 are 1 bit, then only this will be valid. Else like what will happen is that S1, right, is a 1-bit number, that is fine. Now if like if S1 and S0, let's say I'm calling for this one I1. Okay, so if S1 and S0 is 0 1, then only I1 will be selected, correct? The problem here is that let's say if I1 is a 4-bit number, S1 is 0, I1 is S0 is 1, that means this will be 1, 1 and 1 will be 1. But the problem is this is a 1-bit number. So what does Verilog do? It is a 4-bit number, right? So the extra 3 bits get padded with 0. So ultimately, as I am doing a bitwise AND here, so it is doing AND with the 3 bits, first 3 bits of what I1. Okay, so the first 3 bits are automatically getting cleared, so the information is getting lost. So that is the mistake that I realize right now. Okay, so that's why this, right, will not be valid for more than 1 bits. Okay, then you have to like make changes to the code. So I will write here, like that was my mistake on my behalf. I explained this previously. Logically it is correct, but ultimately you are doing bitwise, right? So it is padding the zeros. So warning, this code is only applicable for 1-bit numbers. Okay, if the like if it is higher bit, right, then it is not applicable. So if I now choose a number that is either like 0 or like just a 1-bit number, then it will work, no matter, no problem. But if it is not a 0-bit number, if it is not a 1-bit number, right, then it will not work. So just be careful regarding that. Just be careful regarding that. Okay, so this will be here, right, I cannot give here I equals to something. This will be 1, this will be 0, something like that I have to give, unfortunately. This will be 1 1, this will be 0, this will be 0, this will be 0. Okay, so that is it basically. That is basically it. Now if I run this, right, now it will work. So that was the problem that I was facing. So now I hope you have understood. Like if I run this now, it will totally work. It will totally give me that. Now I am selecting this one, that is 1. I am selecting this one, that is 0. I am selecting this one, that is 1. I am selecting this one, that is 0. Okay, so just be careful about that. So I hope you have understood. Like that's why we have to do things in practical. That's why I am doing this in practical, right? Although theoretically it was correct. So in there as well I will write there that only valid for 1-bit number. This logic equation only valid for a 1-bit number. Okay, so that is basically it. So yeah, now let's move on to the next. Like now if I use that code, right, with conditional operators, it will work. With conditional operators it will totally work. There will not be any problems. So now if I run this, okay, if I just run this now, this will work. Okay, because I had conditional operators, so conditional operators will work. Okay, so conditional operators is like a mux only. So it's like a 2:1 mux. Okay, so what does Verilog do? It treats it as a 2:1 mux. That's it. Okay, the conditional operator, it treats as a 2:1 mux. Now if I run this code, okay, you see I'm able to see the outputs for multiple bits. Okay, so I have selected here, like the first 00 is selected, so 1 is the output, then 01, that is 010 is the output, then 10, that is 011 is the output, then the last one, that is 100 is the output. Okay, so I hope you have understood the point here. I hope you have understood the point. Okay, so that's why this method is more preferable. Okay, so actually internally, right, internally this conditional operator in the synthesizing tool is automatically replaced by a mux only. Okay, so this synthesizer is automatically a mux only. Why? Because let me go back to my writing pad. So if I go back to my writing pad, if you see, like, what is this? Like, if I see a 2:1 mux, so if I have a select line S0, if S0 is high, then it will choose the, if S0 is low, then it will choose the I0. If it is high, it will choose the I1. That's it. That is what my S will do. Okay, that will be our output. So it is basically, this conditional operator is basically a mux only. Okay, so that was about the mux. Okay, now let's move on to the adder. So adder, although we have seen, just let us go through this again, once again. So adder, if I see, this will be the test bench for a full adder. Okay, so this is basically a full adder with Dataflow operator. So here I am doing assign. Okay, just simple adder. This is not a carry look ahead adder. So now if I just run the code and check the output, so if I am adding 0 and 2, I should get 3, right? So I am getting 3. If I am adding this is 5 and what is this? This is 8 plus 2, 10 and 1. So this actually is out of the range, because this is a 4-bit number and like it is out of the range, so that's why the cout becomes 1 here. Okay, so basically what it adds, this is 1 plus 0 plus 1, that is the carry gets 1, then again 1 plus 1, that again the carry gets 1, again 1 plus 1, again the carry generates to 1, and again 1 1. Ultimately, like the Cin is 1 and sum is 0 0 0 only. I hope like this basic addition you can do. Again the same thing here only we are doing. If I'm adding 1 with this, so basically what will happen, again a carry will be generated, like this is adding 1 like 3 times. So what will happen, 1 plus 1 will be 0, then again I'm adding 1, so it will be 1, and I have a carry. Okay, then that carry will be added with this, then again it will generate another carry, that will be added with this, again it will generate another carry, that will be added with this. Ultimately it will be 0 0 0 1, and ultimately I will have another carry that will go into the cout. Okay, so simple adder, 4-bit adder. I hope you understand, like basic things you understand. Okay, now let us discuss about the look ahead one. Okay, carry look ahead, like the output will be same, right? You will not be able to see the difference, but in hardware what will happen, it will be faster, because obviously previously the information was going through many things, right? Many gates, many logic gates and something. So there might be a delay of logic gates, like in real life we know there are delays of logic gates, but here, right, we directly have a logic equation here, so the delay will be lower, but the output that you will see will be same. In the simulator the output will be same, because here, right, we will not track the delays, of course. That will only come when we will actually what do you say, when we will actually synthesize to the hardware. Okay, so that is the thing. If you see, right, I have run a different like test bench, the module has changed, but the output will be same. Output will not change. If you see previous output and this output are all same. Okay, they have not changed. Obviously the output will not change, because like logically we have written everything correct, just the delays will be lower now with carry look ahead. Okay, so just try to model another different type of adder. Okay, so I hope you understood this point. Now next part is for the counter. You can ignore this part. Okay, if you don't understand, like ignore the D flip-flop working. We will understand later on. Okay, in the sequential block, in the like how do you say, behavioral modeling. Don't have to worry, just understand like the hierarchical modeling, right? I'm making a ripple counter, so I hope you have studied that much, like what are counters and what are ripple counters, how to make ripple counters with T flip-flop, so that much you know. Okay, so I'm just simulating here. So for simulation, right, I have to generate a clock. So the test bench generates a clock. So initially the clock value is 0, then this forever is a keyword that I will explain in the behavioral modeling. So this forever means this will always run, and this happens only inside the initial block. Okay, don't worry, skip this, just take my word, this forever will always run in a delay of 10. After a delay of 10, this will always keep on running. That's it. What we're doing, we're just toggling the clock to develop a clock signal. That is what we're doing. And then we are monitoring the output Q, clear, and the we are just monitoring the Q and clear, right? Clock will always toggle. And like I will show you the graphs as well. Okay, so now let's, like this, I hope you understand, like we already have explained the code only. So T flip-flop is made here, then from the T flip-flop we call the D flip-flop. Okay, so I'm not explaining the D flip-flop, we will learn about D flip-flop later on. Okay, so let me do the I Verilog, let me do the VVP. So if you see, like this is the time actually, and like initially Q is 0, at time 34 ultimately, like clear was 1 before, and after 34 time I make the clear to be 0. If the clear is initially 1, right, obviously clock like the counter will not change its state, it will be 0 0 0 only. Okay, so as soon as the clear becomes 0, now the counter starts its count from 40. Okay, then as that what is the time period? Time period is 20, right? Time period is 20. I will show you in the graph as well. Okay, so after every 20 nanoseconds the Q changes its value. If you see here, it like the clear is 1, right? Even though the value was not totally 15, the value here was only 10. If the clear is 1, then it simply resets, it becomes 0. Okay, so that is the case over here. Very simple and very easy. Okay, so like what I wanted to show you is the graph as well. Okay, so I hope this part you understand, like how the counter is working. With graph we will understand this even better. So GTK wave, then VCD, right? This VCD files. So I will show you the graph. If the graph opens, my laptop today is a bit like slow, it is lagging sometimes. So now I hope you can see the graph. So in basics we have C1, we have the Q signal, Q is basically the output, we have the clear, we have the clock. So clock, right, if you see, once the, like it is a negative H trigger, right? So that's why when the clock transitions from high to low, then only we get a response. So Q here becomes 1, then Q becomes 2, 3, reset is 0, So here it is A means it is 10, okay, basically in hex. So suddenly what happens is the reset is high. If the reset is high, then suddenly it resets to 0. Okay, then again here, again the reset is like clock is 1 2 3, like sorry, here again the reset goes low. Again we will not start from here, we will wait for the next negative edge. So negative edge of clock is here, so then we start from 1 2 3 4 and it goes on till counts. Okay, so if the reset was here not high, right, it would have counted till 16 and 15, then it would have reset. So we can I can show you that as well. So let's say I'm doing the reset at a very later stage. So let's say I'm doing the reset, let's say at 300 nanoseconds. So now if I have to recompile this I Verilog, then I have to do VVK, then I have to do the GTK wave. So now if I show you, so now you see, so okay, we are so unlucky that the reset is happening when this is reaching the highest value. So what I will do, I will just make it 350. Okay, I will make it 350 again. So now if I recompile it, okay, not GTK, first I have to show the outputs, right? First to change the output false, then if I do GTK wave, so now if you see right here, although the reset is 0, so automatically it resets to 0. That is the logic basically of a counter. So it is up counter, so automatically it resets to 0. So that was about it for this lecture. So I wanted to give you few homeworks. Okay, few homeworks is the exercise question. So we will go to the exercise question. So counter and logic, all those things we have understood. So I will leave you with the chapter 6 of the Samir Palnitkar book. So try to solve this, and in the next lecture we will solve all the exercise problems. Okay, and that will be the end of the module 1. If you have enjoyed until this part of the video and this lecture series, make sure to comment on the first video and make sure to like the videos if you are enjoying, if you are understanding something meaningful, if you are understanding like if you had a bit of difficulty in this topic and if you're understanding, right, please hit the like button. That like helps us, it appreciates the like our effort. Okay, so thank you for watching and I hope to see you in the next video. Until then, happy learning.